and that's apparently important for accurate climate modeling. So that all that sensitive dependence on initial condition stuff. So anyway, you can use this technique in a number of ways. And it's worth noting just because it's actually very fast on the old hardware. The cost for an algorithm like the direct Coulomb summation, where the majority of your time is doing reciprocal square roots and things like that, the cost of adding the numbers in compensated summation just at the point where you do the accumulation here. So it would just be this little plus equals would become a little function call or run that algorithm. It's maybe only 10-15%. And the same thing could be done in molecular dynamics for adding forces. You can use either one. I think we did a test in NAMD where we used compensated summation and double precision arithmetic just for the accumulation of forces at the end of the molecular dynamics non-bounded kernel, and it was 10 or 15% slower than just doing it in single precision. So the thing to keep in mind is in almost any real floating point kernel you do, only about half of the arithmetic is floating point arithmetic anyway. A lot of times you have various loop overheads and things like that. And so the cost of doing the summation with more precision is often very low relative to the rest of what you're doing. So as you learned yesterday, there are various things we can do to remove redundant arithmetic from the direct Coulomb summation kernel. The main thing to realize about this particular kernel is the majority of our work component comes from the evaluation of different lattice points. So we have 20 times as many lattice points as atoms. And so that makes this a very arithmetic-intense kernel from the outset, much more so than some of the things you'll hear later today. And because the lattice points are the largest number of, they contribute in the largest magnitude to the size or scale of the computation, this is probably the most important thing for us to optimize in terms of avoiding memory references. And so the first thing we do with this algorithm from the very beginning is we compute lattice coordinates on the fly. And so we do arithmetic to calculate where those lattice points will be. A person might, I have people say, well, why didn't you just pre-compute all those lattice point coordinates? Well, if we compute them ahead of time and load them for memory, those are extra global memory reads we would have to do. And so this is the first thing to realize. To be GPU friendly, we want to do arithmetic. We want to avoid memory references. So if you have an opportunity in your own kernel to compute something rather than look it up, it's probably a good idea. And so in this kernel, it definitely is. And since the calculation is very regular, we can do all kinds of optimizations without arithmetic. Yes?
So intuitively, you would think that you need the maximum and the minimum would probably be in the near vicinity of the molecule.
Yeah.
You would be placing your ions in the near vicinity of the molecule. So it seems like away from the molecule you don't have to have a lot of resolution. You could have a non-uniform mesh. Say you could have maybe 10% here and then 90% around the molecule. So, I mean, would that optimization be useful to do? Because then the problem is then you have the non-uniform metrics. It's not just grid size.
You could definitely do things like compute different regions of space with different spacing values or with different precision and all kinds of things like that. For the particular problem we were solving, we were basically restricting the bounds of that grid to very tightly contain that target molecule. So we really didn't have much opportunity to do anything tricky like that. But if you were computing that potential map in a much larger region of space, yeah, I would totally agree. It makes no sense to have overly fine lattice in areas where nothing is changing very rapidly, where it's very smoothly changing. So you could use a multi-resolution approach or something like that. So the key things that we have to decide for this direct Coulomb summation kernel are what memory systems to store the atom data in. So you guys already know the answer because you've seen the kernel earlier this week, but that's the big question whenever you write any kernel is where am I going to store my operands? Are they going to be in constant memory? Are they going to be in shared memory? Are they going to be in global memory? Or can I use the texture unit? Somebody asked me yesterday, what's the difference between the texture memory and shared memory and these other things. The texture memory is an interesting example because so GPUs do rendering of things that have complex patterns. That's part of their daily job. And so if you look at this carpet, you see a little pattern. And in computer graphics, it's often easy for them to basically take a picture of some replicated tile and then apply periodic conditions to it. And then as you're drawing, you do basically a little lookup to see what color the carpet will be at any given point. And then, so they basically built dedicated hardware to do this type of table lookup, to make it so that even when you look closely at that carpet, it continues to look smooth rather than pixelated. The hardware has, the texture unit has dedicated hardware for doing things like interpolation, range clamping, and various other things. And so, if your algorithm needs interpolation or needs range clamping or needs automatic periodic lookup conditions and things like this, the texture unit may be a better match for your particular problem than the other memory systems are, because the texture unit will do all this for you for free. There's, it's sitting there unused otherwise. The texture unit is also good for cases, especially on older hardware, where you have a random access pattern. So if you don't know which order you're going to read elements in an array or something like that, you can fetch those from the texture unit, and it will improve your effective memory bandwidth because it has a small cache. The cache isn't big enough for anything like reuse, but it is big enough so that many threads within the same warp accessing randomly organized elements in the global memory, what would have been very slow or uncoalesced, with the texture hardware will become coalesced accesses. For the particular problem we're solving, we don't need any of that. All we need is basically consecutive reads and long loops and consecutive reads. And all we are attempting to do is basically provide peak bandwidth to the kernel so it can loop through all of those atoms as quickly as possible. And so in our case, the best choice for that is either constant memory on the older hardware or to use the L1 cache on newer devices like Fermi. And so that's sort of the obvious choice. You could also do it in shared memory, basically loading blocks of global memory into shared memory collectively, processing them, and then loading another tile. For the multiple to bihuckle, that's what we did. And that worked pretty well in that case because the arithmetic was complex enough that we spent more time doing those reciprocal square roots and exponents and things like this than we did executing instructions related to all that array indexing. But in a kernel as simple as direct Coulomb summation, there's not really enough arithmetic there to cover all of this extra array indexing math. So it turns out that basically only the simplest approach in terms of the indexing complexity works out. So that would be constant memory or the L1 cache. And then the other thing we can do to improve direct Coulomb summation is exchange some of our parallelism for better single-thread performance. And that turns out for this kernel to be a pretty good choice because we have such a large number of lattice points to compute. We have ample parallelism, so it's easier for us to sacrifice some parallelism in terms of the number of lattice points or the number of atoms that we're computing against those lattice points in order to get a little bit better single-thread performance. And you've seen this plot before. The main thing to realize is in order for the GPU to perform well, we have to have enough work to fully saturate it. So depending on the problem size, down in the range of 100 or 1,000 atoms, we basically don't really have enough work to have that GPU fully utilized. And so we may take a different approach in terms of the degree of loop unrolling or how much parallelism we trade for single-thread performance, depending on the problem size we're actually trying to solve. So for small problems, it may not be appropriate to sacrifice any parallelism. It may be better to keep what parallelism we have and guarantee that all of the processing units on the GPU are fully utilized. So let's see. And so the sort of schematic view of this calculation looks like this. We begin with an empty grid of potentials, and you'll see that there are it's basically padded out so that the array in memory, there's a multi-dimensional array in memory, and we've padded it out in both x and y in such a way that it is an even multiple of the thread block size. And this does a couple of things for us. It simplifies the array indexing inside that kernel. It guarantees that memory accesses will be coalesced, so not only for the first row in the array, but then the next row, the first thread in the next row begins exactly on thread block boundary and exactly on a memory coalescing boundary. And by arranging that up front, we know that we can never have a condition where those memory accesses become non-coalesced, and we don't have to worry about sort of offsetted addressing or any other complication. So you guys learned about memory coalescing in some detail, right? Previously? Okay, good. And so if we do loop unrolling to do multiple grid points per thread, the main thing we have to do is make sure that when we step through memory in that unrolled loop, that we are stepping by a stride length that is equal to or greater than some multiple of the memory coalescing size, so that every time this thread processes another lattice point, it is accessing a lattice point that happens to fall exactly on the right address to enable memory coalescing for the next iteration. So that's the only other trick here that one has to realize. So when we do that calculation and we pull those results back from the GPU, ultimately on the host, we will, if these results that we're padding can't be used for anything, we have to peel those off. So that's an extra piece of work that we have to do on the host. And what's interesting to note is, depending on your application, if you plan ahead enough, usually when you're taking an existing piece of code that you guys are already working with, I've already heard that many of you have a bunch of Fortran code in hand that runs, and you're wanting to add GPUs to the Fortran code. So this is a case where you're often going to end up in a situation where the existing code doesn't know anything about GPUs, doesn't know about these funny memory padding requirements or any of that stuff. And so you end up having to do some sort of post-processing to remove things like these padding bytes at the end of different arrays. If, on the other hand, you're willing to make some adjustments to your original code, you can often set it up in such a way that the host code will live with this padding being there. So you can add a little bit of indexing arithmetic in the array access code in your host side of your code, and basically teach it to deal with a padded or strided array like this. And then by doing that, you can eliminate the overhead of having to peel that off. You just take it as is, straight back from the GPU on the host, and you work with it the way that both the host and the GPU like it. If you have the opportunity to do that, that's probably a good idea, and I'd say that for two reasons. One is then you get rid of this, what becomes otherwise a potential bottleneck in your code. If it's a big enough array, the CPU is not very fast at doing those copies. The other is CPUs are getting both SIMD units like SSE. You know, we have SSE now on everybody's PC that works on 4-element vectors, but the next generation CPUs will have 8-element SIMD units, so they can do twice as much work at a time. And the next generation Intel and AMD chips all have onboard GPUs of their own. They're going to be very simple, very low performance GPUs relative to the type of NVIDIA GPUs that we've been using to date. But those will be able to work on much wider vectors of numbers. And so you'll have many of the same padding constraints and things that you have with the GPU. In fact, I would say that the current generation of GPUs are far more forgiving